Our immune system is a marvel of biological engineering, designed to protect us from a myriad of threats. However, what happens when this powerful protector becomes misdirected? What happens when its defense mechanisms, instead of safeguarding us, begin to cause damage? Today, we introduce the 4 main types of hypersensitivity reactions, and we'll take a deeper dive into the intricate cellular and molecular mechanisms that drive these immune responses. Our journey into the specifics begins with hypersensitivity reaction type 1. Upon initial encounter with a seemingly harmless substance, such as pollen, dendritic cells carry the allergen to regional lymph nodes, where they present it to naive CD4 T cells, activating their differentiation into T helper 2 cells. When B cells encounter T helper 2 cells, they undergo class switching to produce immunoglobulin E antibodies. Though this initial exposure doesn't cause any symptoms, it's a critical priming or sensitizing event. The B cell, now activated, begins to churn out immunoglobulin E, setting the stage for future allergic reactions. Following immunoglobulin E production, these antibodies don't float freely for long. The newly synthesized immunoglobulin E antibodies travel and bind to specific high-affinity receptors, called Fc epsilon receptor 1, on the surface of mast cells. The mast cell, now adorned with these immunoglobulin E molecules like an array of antennae, becomes sensitized. It's now a silent sentinel, awaiting re-exposure to the specific allergen. When the same allergen drifts back into Immunopolis, it walks straight into a trap. On the surface of every mast cell, hundreds of immunoglobulin E antibodies are already standing guard, each one specific for this very intruder. The allergen cross-links neighboring immunoglobulin E molecules, pulling their Fc receptors together like triggering a molecular alarm system. Inside the mast cell, powerful signaling pathways ignite in an instant. Within seconds, the mast cell degranulates, explosively releasing histamine, proteases, and inflammatory mediators into the surrounding tissue, transforming a harmless re-encounter into sneezing, itching, wheezing, swelling, or even life-threatening anaphylaxis. So this describes the immediate phase of type 1 hypersensitivity reactions. However, hours later, a late-phase reaction can occur. This phase is characterized by the recruitment of additional inflammatory cells, such as eosinophils and Th2 cells, which release newly synthesized mediators, including cytokines and leukotrienes, thereby sustaining and amplifying the inflammatory response. Now, let's shift our focus to type 2 hypersensitivity, where antibodies target self cells. The mechanism of cellular destruction varies according to the type of culprit antibody. When immunoglobulin G antibodies coat a red blood cell, for example, effectively tagging it, macrophages, equipped with Fc receptors, recognize the Fc portion of these bound immunoglobulin G antibodies. This recognition triggers phagocytosis, where the macrophage engulfs and destroys the antibody-coated cell. This process, often occurring in the spleen, is a major contributor to conditions such as autoimmune hemolytic anemia, in which the body's own red blood cells are mistakenly destroyed. Another destructive pathway in type 2 hypersensitivity is complement-mediated lysis, often associated with immunoglobulin M antibodies. When these bind to antigens on the cell surface, they can activate the complement cascade. This cascade culminates in the formation of the membrane attack complex, which punches holes in the target cell's membrane. The cell, like our red blood cell here, becomes compromised and ruptures, leading to direct cell lysis. This mechanism is particularly relevant in transfusion reactions, where incompatible blood cells are rapidly destroyed. Beyond direct cell destruction, type 2 hypersensitivity can also manifest as receptor dysfunction. In conditions like myasthenia gravis, antibodies block essential receptors, such as the acetylcholine receptor at the neuromuscular junction, impairing nerve-to-muscle communication and leading to muscle weakness. Conversely, in Graves' disease, antibodies stimulate receptors, specifically the TSH receptor on thyroid cells, leading to overproduction of thyroid hormones. In both cases, the antibodies don't necessarily kill the cells but rather alter their normal physiological function, highlighting the diverse pathological outcomes of type 2 reactions. Moving to type 3 hypersensitivity, we introduce the concept of immune complex formation. This occurs when soluble antigens bind to circulating antibodies, forming antigen-antibody complexes. While small complexes are usually cleared efficiently, If there's excess antigen or impaired clearance, they can grow larger and persist. These floating clusters are the precursors to tissue damage, as their deposition in various organs is the hallmark of type 3 reactions. Immune complexes tend to lodge in sites where filtration occurs, such as the kidney glomerulus, or in areas of high blood flow and turbulence, like joints and skin. Once deposited, these complexes act as potent activators of the complement system, which in turn recruits inflammatory cells, particularly neutrophils, initiating a cascade of inflammation and tissue injury at the site of deposition. Deposited immune complexes are often too large or bound to tissue surfaces, making them inaccessible to neutrophils for effective phagocytosis. In their attempt to clear the complexes, they inadvertently release a barrage of lysosomal enzymes and reactive oxygen species into the surrounding tissue, causing significant collateral damage and inflammation. This frustrated phagocytosis is a key driver of tissue injury in type 3 reactions. Finally, we turn our attention to type 4 hypersensitivity, which is T-cell mediated and delayed. During the first exposure to an antigen, a dendritic cell, acting as an antigen-presenting cell, processes the antigen and presents it to a naive T-cell. This interaction activates the T-cell, leading to its differentiation into antigen-specific memory T helper 1 cells. These memory T-cells are now primed and ready to mount a robust response upon subsequent encounters with the same antigen. The effector phase of type 4 hypersensitivity occurs upon re-exposure to the antigen. The previously sensitized memory T helper 1 cells recognize the antigen and become activated. They then release interferon gamma, which acts as a powerful activator of macrophages. Activated macrophages release a range of inflammatory mediators, driving macrophage-driven inflammation and tissue injury. This delayed, cell-mediated response is why reactions like the tuberculin skin test take 48 to 72 hours to develop. In cases of persistent or difficult to clear antigens, type 4 hypersensitivity can lead to granuloma formation. Here, macrophages and T-cells encircle and wall off the persistent antigen, such as Mycobacterium tuberculosis bacilli. This forms a granuloma, a localized collection of immune cells that attempts to contain the threat. While granulomas can effectively limit the spread of pathogens, they can also cause significant tissue damage and dysfunction, as seen in diseases like tuberculosis and sarcoidosis. It's a testament to the immune system's persistent efforts, even when those efforts lead to pathology. Alright, let's sum this up. In the city of Immunopolis, chaos can be sparked by 4 different mechanisms. When type 1 mast cells, armed with allergen-specific immunoglobulin E from a previous encounter, unleash histamine, which may cause swelling, wheezing, and shock. At the same time, type 2 antibodies mistakenly tag the body's own cells with immunoglobulin G or M, summoning complement and killer cells to destroy them. Elsewhere, type 3 antigen-antibody complexes accumulate in blood vessels, joints, and kidneys, triggering an inflammatory flood. And days later, type 4 T cells return to the scene, releasing cytokines and activating macrophages to produce delayed tissue damage. 4 different immune battles, all driven by the same tragic error. The immune system has turned its powerful weapons on its own body. Hypersensitivity is not weakness, it is immune power without control. Each of these reactions, from the immediate allergic explosion to the delayed granuloma formation, represents a misdirection of the immune system's formidable capabilities. Understanding these mechanisms is paramount for clinicians and researchers alike, as it enables us to better diagnose, treat, and ultimately prevent the suffering caused by these powerful yet sometimes damaging immune responses.